Joseph for Q&A.
All right, well, welcome everybody to CC Colloquium for March 31st. Hard to believe that March is already over, 2021. I'll turn the floor over to Steve Semken to introduce our speaker in just a moment. Just before that, there are no CC leadership announcements, but I do want to give a quick plug to our colloquium next week, which will be a bit unusual. It's labeled on the schedule as Mars 2020 Perseverance Panel. So we're going to have a little bit of a group presentation anchored by our own Jim Bell and Minnie Wadwa, talking about the Perseverance lander, the geology, some of the sample return planning. We think we're going to have somebody from the entry, descent, and landing team at JPL to come talk to us about the whole landing process and adventures there. And we're going to structure it with a lot of Q&A time for folks to ask questions about the Perseverance rover and the Mars 2020 mission. So that should be kind of fun and different. And so look forward to seeing you there. And so without further ado, I'm happy to turn this over to Steve Semken to introduce our speaker.
Thank you, Ariel. And it is indeed my pleasure to introduce my longtime colleague, occasional field associate, always good friend, and currently not too distant neighbor. She's basically just behind me up on top of the Mogollon Rim looking down. Dr. Nancy Riggs, who's a professor of geology in the School of Earth and Sustainability at Northern Arizona University. Nancy got her BA in geology from the University of California, Santa Barbara in 1979, Master of Science in Geology from the University of Arizona in 1985, and her PhD from the University of California, Santa Barbara in 1991. Nancy is a fellow of the Geological Society of America. Her research addresses how tectonics can be read from volcanic and sedimentary rock records, and it ranges from exploration of the interaction of volcanism and tectonics that's seen in volcanic successions to the interaction of volcanism and paleotopography that's seen in sedimentary successions and their relation to tectonics, and also includes what she refers to as just plain physical volcanology. Nancy has done extensive research all across Arizona, into Mexico and other parts of the world as well. Her presentation to us today is titled, "When Plates Collide, Turning Boring Beaches to Violent Volcanoes." That's a great title. I'm most happy to present Dr. Nancy Riggs. Nancy, it's all yours.
Thank you. Thank you very much. Okay, so I will share my screen and there we go. Alrighty, so thanks very much to Steve and to Ariel for inviting me, and to everyone for showing up to listen to, well, boring beaches. No, not very much about boring beaches today, I will say. Ariel and I had a little exchange, because I started out with a very technical title, and he asked me to please remember that many people in the audience don't necessarily have a whole lot of geology background. So this is what we came up with. On the side of the screen there is a cartoon that Bob Stern, who's sort of the guru of understanding a lot of plate tectonics and especially subduction, he passed this on to me. And it's towards the bottom, if it doesn't make a whole lot of sense to begin with. The idea is that the acorn-headed person is sort of acting like subduction, and he's pushing himself down into the earth, being a subducting plate, and he's completely disrupting his noble professor there sitting aside. So let's see. There is a way for me to advance slides. Here we go. What I want to do is talk about firing up a volcanic arc. What does that mean? How do you do that? Volcanic arcs usually sit on top of subduction zones. Not always, but it's very common. But subduction has to start sometime. And when you learn about volcanoes and you learn about volcanic arcs and you think about the Cascade Mountains or the Andes or these beautiful places like that, you are told there is a subduction zone, and it's true. But you can't just invent a subduction zone. It has to start somehow. So that's what I want to talk about today. And I want to talk about it with regards to our very own continent, which is North America, of course. The quote at the bottom, because subduction initiation is a tectonomagmatic singularity with no active examples. Reconstructing it is challenging. And that's to say that we don't look at any place on Earth right now that we are confident that subduction is starting. And we have some ideas about places that it might be very young or that it might be going to start. But in fact, it's hard to sort of say this is where it starts and especially why. So I'm going to feed you some jargon, and I'll try and keep the jargon to a minimum once I'm off and running, but I want to tell you the things that I'm going to tell you about. Pangaea, you have probably heard of, the great big supercontinent, but we were part of Pangaea for quite a while, and so that becomes important. I need to tell you what I mean when I say subduction initiation. How do you start a subduction zone? But it's all because in southwestern Laurentia, which is us, which is North America, between about 300 and 250 million years ago, we transitioned. We were a land of boring beaches. We transitioned. We had a San Andreas-like fault, and then we had plutons, volcanoes, sediments that record volcanoes. So we can sort of sort through all of those things and decide, what does that mean? What can we say about the initiation of subduction there? Okay, this is our blue marble, and you've seen many gorgeous pictures of the planet. And I want to just point out a couple of things. Let's see, I'm going to try. Well, I'm gonna hope that you can see my cursor as I move it around. So you've probably seen pictures like this and these deep, deep colors of blue that indicate their subduction zones all around the Pacific Ocean. So that's good. We like subduction zones. Subduction zones give us volcanoes. Oops, sorry. On the east coast of North America, if you've spent any time there, you know that there are miles and miles and miles and miles of beaches. And some of that can be attributed to the fact that North America is pulling away from a spreading center, which is out here in the middle of the ocean. The spreading center is not too important to our story. The other thing that I want to make sure is clear is the San Andreas Fault. And this is just like a line drawn. It's not exactly where the San Andreas Fault is, but you probably heard about that. Goodness. And it's a very important sort of tectonic setting as well. So if you sort of keep in mind these passive margins where nothing's going on and active subduction zones where one plate is diving underneath another one, and then a transform fault where two plates are moving by each other, then you're in good shape. Okay, I want to shout out to Steve Reynolds, who a month ago gave a talk about basically, the geologic history of your part of the world from Mesozoic time on. And I'm going to talk a little bit, not very much about this neck of the woods, but I suppose if we'd been thinking really intelligently, I would have gone first and then he would have taken up where I would have left off. But this is sort of the precursor. This is the prequel to Steve's story. I refer to deep time. And when I say deep time, I again mean this sort of late Paleozoic and early Mesozoic time, 310, 300 to 250 million years. The background slide, I'll show you it in a little more detail in a minute, is part of the whole supercontinent of Pangaea. And I'll just in a sec, my next slide will show you what are the different parts of this whole Pangaean supercontinent. It turns out that you can't very easily move plates around, move continents around, move oceans around. You can't move things around without affecting a whole lot of other things. So it turns out that the southwest margin of Laurentia, of North America, was very much affected by things going on elsewhere in the world. The last sort of like word point down there is that people who do study plate tectonics usually do it in the ocean. They don't think about continents. The little video going on in the corner there is plate tectonics through time. And you probably know that the red lines with the barbs on are subduction zones, and the blue lines are mostly these spreading centers. And really, rather than focusing on anything, what I want you to notice about those red barbed lines is that they kind of come and go. There's one, and then it's not, and then it joins something else, and it happens all at once. That's really the sort of the main thing. And here we are at our present configuration. The problem with these reconstructions, and the problem that we have to sort of keep in mind thinking about southwestern Laurentia, southwestern North America, is that all these things don't happen all together. They happen in one place and then they happen in another place, and then these two things join together and they become a beautiful subduction zone. But it's very difficult to look at a whole entire margin and say, this million year, it was this thing, and this million year, it was something else entirely. It's very sporadic. Okay, so here's Pangaea. And just some things that you might have heard of. Well, right now it's because you're listening to me, you've heard of Laurentia, which is the Northern European, North American continents up here. By the way, you live right there. Gondwana in the south, South America, Africa, Australia, Antarctica, India, the big continents. When those collided, we got our supercontinent. I'm going to be referring to Gondwana, not very much, but just sort of keep in mind that it's this big southern continent. And we are Laurentia, we are this big northern continent. And by the way, all these sort of mountainous countrysides that I've just highlighted in the red squiggle is the collision zone. Collision zone might turn out to be fairly important for what I'm trying to figure out here. Okay, so here's subduction initiation. Bob Stern, the guru, in 2004, put together this paper, and it had a number of things: how to do this, how to start a subduction zone, how to make an ophiolite, how to make plate tectonics make sense and have fun in the process. And he differentiated between induced and spontaneous, and he provided these sorts of ideas about what could cause a subduction zone to start. And none of these are hugely important specifically. I just want to show you that sort of like, this is where it started, and these are these ideas. In these little graphics, the black lines are ocean plates, and the crosses in these sort of blobs are continents. All right, then, some further ideas is that some people started to say, well, maybe what we're mostly looking at is a density contrast, right? So oceanic crust is more dense than continental crust, and old oceanic crust is more dense than young oceanic crust. And so this is a little bit sort of, I don't know, modified, more discussion about it, just to say, okay, how should we look at these things? Let's look at it in terms of density. And that sort of worked. And then people started saying, well, what if you look at sort of external forces? Are things being driven together? Is there pressure from plate motions? Is that more what's sort of doing it than density? Or are they both working together? So there are these two things that don't necessarily work separately, but people were trying to fit the subduction zones that they were used to into this kind of, is it spontaneous? Is it induced? So induced was modified to forced, which is to say external forces. In this particular case that we're going to have to deal with today, the one issue is that we're not dealing with oceanic crust, or if we are, we're dealing with one plate that's oceanic crust and another plate that's continental crust. So I added on this little addendum to say, well, what happens if you have equivalent density? You have very much this external shoving, but you can't look at it and say you have higher versus lower density. What's that going to do to it? So I'm going to pull us out of Laurentia for just a second and take us down to the South Island of New Zealand, where this is going on. This is one of these places that we look at and we say, this is kind of suspicious. If you've been to New Zealand, you know that it's this lovely island, and you may know that there's a great big fault running up and down the west side of the South Island, and that's the Alpine Fault Zone. And when it comes offshore, it turns itself into a subduction zone. And lots of people like this situation a whole bunch, because here's the oceanic crust and here's the continental crust. So maybe this is a situation where these two very different density, but also this pressure being put on them, are both working together. That's an idea about that. And as I say, its importance is that it is one place where it looks like there's oceanic crust subducting down underneath continental crust. This is what this little blue blob is in here, is the Australian plate, the ocean part of it, diving down underneath New Zealand. So this idea of subduction initiation is pretty well established, and it's recognized in ancient examples and maybe recognized in modern examples. There is one tiny little volcano right in here that's part of this system. It's not doing very well for its volcanoes yet. The only other thing that I want to tell you about this business of of initiation is that people say, well, if you have a strong plate, a strong continental plate, you probably, and it's this force, these forces pushing on the plates to make subduction happen. You're probably looking at this, which I've circled in yellow to say, there's nothing going on to sort of spread things apart. There's lots and lots of contraction. So lots of rocks being shoved together. So I'm going to suggest that's maybe what we're going to see here. Here we go. Here is Laurentia. Remember from the previous slide, not that one. And down here is Gondwana. This is a very, very busy map, and I don't want you to pay any attention to anything except the colors. We have Laurentian continent up to the north. We have the Gondwana continent to the south. We have this blue line, which is basically the collision between those two continents. And we have the pink words, which are when that happened. This is in Mississippian time. This is Pennsylvanian time. This is Permian time. So you can sort of look at this as a margin as Gondwana sort of smashed into Laurentia, this kind of zippered, just zip this thing up. And you've got a continent being formed in here. This becomes important, this late Permian, because that's when we're starting to talk about. Okay, here is North America, Laurentia, southwestern Laurentia, at about 300 million years ago. And you are here-ish, yes, there's Arizona for us. We have lots and lots of passive margin in here at this time, but we're starting to see some strike slip faulting going on. So this is what I call the San Andreas-like fault. The biggest difference that I probably shouldn't tell you, but I'm going to anyway, is that the San Andreas fault goes the other direction, so that Los Angeles is trying to make its way up to San Francisco, whereas in this case, Los Angeles would have been escaping San Francisco. So here's these arrows show you which side of this fault was moving in which direction. Good transform fault. What I need to tell you about is two blocks of Permian arc rocks, those plutons, those volcanoes that make up an arc. And then I'm going to tell you a little more about some sediments that are a little bit farther north, and then I'm going to try and put it all together and figure out what it all means. So here is this thing called the Caborca block. And on this diagram, it's this bit of ocean, of land sitting out in the ocean because nobody is quite sure what to do with it. So here it is down here. It presently resides in southernmost USA, but especially in sort of the state of Sonora, and I wouldn't even say centered, but the region of, of Caborca, Sonora. The other one is up in Eastern California, and it's called the El Paso Mountains terrane. So I want to describe the Sonoran example first, and then I'll tell you about the El Paso Mountains, and let's see what these things can tell us. If we're going to look at igneous rocks, we need to get some information from them. We need to know how old they are. Can you actually take an igneous rock? What can you do about dating it? You've probably heard lots about dating igneous rocks, and this is no exception. We take out little zircon crystals, and we love zircon crystals because they are full of uranium, and the uranium decays to lead, and we can measure that decay, and we can get a very good idea of the age of the rock the zircon came out of. So we can date igneous rocks really nicely. We can look at the sedimentary rocks because whenever igneous rocks sit at the surface and erode, they turn into sediments. The other thing that we want to look at is what I call the nature of the igneous rocks. And by that, I mean, did these igneous rocks come from continental crust or did they come from oceanic crust? How can you tell? Is it possible to tell about oceanic and continental crust? Where were the volcanoes? We gave up passive margins and boring beaches. We need some volcanic action here. So this is Mexico. It's a beautiful, beautiful part of the world. It's obviously reminiscent of your guys' part of the world because it's about the same elevation and it's just a little farther south. These plots are not meant to make you crazy and they're not meant to sort of dull your brain, but they are meant to give you a little bit of information about age data. So the picture with the Swiss Army knife there is what that pluton actually looks like. Its name is Los Tanques. And we dated a bunch of different samples of it just to make sure that one part of it wasn't especially older or younger or had something wrong with it that would make the zircons not behave properly. And we got a range of ages. My own personal favorite is this one. You can see all these red blobs, and they're kind of dispersed around. And that's got to do with what the zircons may have gone through since they were born. This sample, these red blobs sit right on top of each other. So this is the Los Tanques Pluton, and its age is about 273, 272 million years. You can tuck that age away if you're good at memorizing things. Just remember 275. It's a very friendly number here. Just very close to that is a sedimentary succession called the Monos Formation. And I had a grad student a few years ago who we've just recently got a paper out in Geosphere about this, but he had a good look at the Monos Formation and he decided sort of what the succession of rocks was. What kind of environments did they start in? He thought, well, there's these mass flows, these subaqueous turbidite mass flow deposits at the bottom and miles and miles and miles of carbonate at the top. But some parts of it are full of volcanic fragments, and that's what's shown on the lower right. These LV means volcanic lithic. These V is pointing to little tiny vesicles inside of this rock. And so if we can't have the volcanoes, at least we can have the material that came from volcanoes and say, all right, the volcanoes were not far away. We did the same kind of looking at the zircons. When you look at zircons in a sandstone, then you take all the zircons you can and you start dating them one by one by one by one by one. And you say, well, what is the most common number that we have in here? And there's that 274, 275 number again, right? So this formation, very politely, is about the same age as the Plutons. So in this sort of summary figure over here, Steve said, okay, here's a range of some Plutons in Mexico. And sure enough, there's the age of the same age is fitting right in there. So we can't say for sure this zircon crystal came from that Pluton, but we know at least there was certainly magmatic activity. Moving up section a little bit to this antimonio formation, we found this lovely conglomerate that was absolutely full of volcanic and sort of subvolcanic clasts. You know, because a volcano sits there and does its beautiful thing, but underneath it, there's some material that's crystallizing slowly but surely, and all of that stuff can be eroded. So we pulled the zircon out of all of these clasts, and here's this range again. It's a little bit older and a little bit younger, but it's that same exact range. So we think we've got pretty good evidence to say there was a volcanic arc in this region at this time. Okay, if you don't know geochemistry, just like plug your ears and close your eyes for just a second. If you do know geochemistry, I feel like I need to show this to you to say, no, really, we were doing the right thing. We looked at all sorts of different types of geochemistry, both rare earth elements and isotopes and just plain major elements, and came up with these different things. And I don't want to spend time sort of explaining this. This really is for the people who know geochemistry. We have ourselves rocks that were crystallized in continental crust. This is what we can look at, this sort of combined bit of information and say, yeah, the continent was alive and well. Okay, so when we started out, we had to say, you know, how old is the magmatism? This is what we're trying to answer. How old is the magmatism? Can we date the rocks? What do we find out? And we know that there's detrital zircons, and there's zircons in the plutonic rocks, and there's zircons in the volcanic clasts. And they're as old as 280, but they're give or take that 275 magic number. We need to know, are they continental? And again, we tell by this geochemistry. Yeah, they are. They're continental. That's good. Do we have evidence of volcanoes? Well, we don't have the volcanoes themselves, which is truly unfortunate. The trouble with volcanoes is they build up and they erode down, of course. So we don't have volcanoes, but at least we have volcanic clasts. Okay, let us scoot ourselves northward. This diagram shows the continental arc. It shows sort of the big tectonic setting in southwestern North America in Pennsylvanian time. So we've been down here in Caborca. We're going to scoot ourselves up here to the El Paso Mountains terrane. The only other thing I want to point out in here is that the author, Jason Salibi, has pointed out that the continental truncation is right there. And what he means by that is what we're doing in here is going from continental and continental to continental and oceanic. Okay, so this is a place somewhere in here where there is a transition between the same North America, the same Laurentia over here, but what was on the other side. And in the south, what was on the other side was continent. And in the north, what's on the other side is ocean. So this Pangaea ocean basin. Okay, this is the work of Robinson Cecil at Northridge, at Cal State Northridge. And she did a whole bunch of dating of volcanic units, lots and lots and lots of intrusions, small things to big things, lots of ranges of compositions, some very deformed. A month ago, Steve told you that rocks enjoy deformation, which may be true, but sometimes their zircons don't. So the plutons are deformed in places, but nonetheless, she was able to pull some really, really nice data out. And lo and behold, there's a number that you probably are getting tired of by now. There's that 274, 275, that same age of stuff that we've been looking at here. More geochemistry. Close your eyes for a second if you need to. Everything that's in this sort of orange color and stars is the El Paso Mountains terrane, mixed in with the Sonoran data. So it's sitting very similarly, just tucked in there with all the Sonoran data. They're pretty similar rocks. Okay, the other thing that we have, luckily, is more sedimentary rocks. And it's something called the Hollan Camp formation. This is a master's student by a student of Robinson's. And the only thing to show you in here is that, it's, again, pretty cool countryside out there. Stacked rocks, they look just like sedimentary rocks. This particular photograph in here, it's a photograph of a thin section, and it's got lots and lots of little fragments to show you that it certainly has a lot of volcanic material in here. All of these thin little white things are all plagioclase feldspars. This is a volcanic rock. So there was certainly a lot of volcanic material shedding in. We looked at the zircons. We had a maximum depositional age. That's what this MDA stands for. 270. You're getting the hang of this. Okay, the last place is just to move a little farther north from El Paso. Don't worry about the details of this, but what I want to tell you and call your memory back to is that these are two. This is my student Emma Lotus, and sorry, there we go. She put together these two panels to say, okay, well, here's early and middle Permian and then late Permian. Here's a thrust fault. Here's another sort of a thrust fault. Here's this sort of arching and folding of units. Remember back to when I was talking about different things that you might expect around a forming arc. If you have this induced, this forced kind of subduction, you might have folding and thrust faulting. Here it is. So that's these lovely purple things. And here in this sort of brownish color is where the arc was developing. So we have a bunch of igneous rocks and a bunch of detritus, and we can start to make some inferences. In this part of the world, that oceanic crust, that ocean basin, that Pangaea ocean basin, was subducting under continental Laurentia. That same magic 275 number, give or take. Usually when magmatism starts, when subduction starts, you find some really characteristic, really basaltic magmas, and we don't see those. We've never been sure why. We do see folding and thrusting in the upper plate. We do say, well, okay, here's this suggestion of strong continental crust. So we probably had that forced initiation of subduction, at least up in the north. Okay, so here are our two spots. And these two spots are quite a ways from each other. And they are both suggesting that magmatism and subduction was alive and well by 275 million years. Now you have to think about that little video clip where different bits of subduction sort of came and went, and whole entire sections, long segments, all of a sudden appeared out of nowhere. I would suggest that that's not quite the case in reality. right? So here's where we know it was going on at 275, and here's where we know it was going on at 275, but not anywhere in between. We haven't seen any indication in here that there was magmatism of that age or farther north into the Sierra Nevada. The other problem is that we have another side to the arc. There's the rocks that are sitting inside the arc itself. There are the rocks like such as the Monos Formation that are on the ocean side. But what about the other side of the arc? What's going on the continent side? So this is just a little slide to say, okay, here's the downgoing ocean slab. Here's the continental slab. Here's the volcano. This is the stuff we've looked at already. What about out here? What about back here in Western Arizona and Northern Arizona and Southern Arizona? What was going on here? So we can look at the Kaibab limestone. If you have not seen the Kaibab limestone, then you have not been in the field with Steve Reynolds. This is what it looks like in the Grand Canyon. This is what it looks like in Steve Reynolds land. Southeast of you guys, down southeast of and east of Tucson, there's something called the Rain Valley Formation. And the fossils below it anyway suggest that its age is a little bit younger than all of this. But at least if there's volcanoes going off at 270 to 265 million years, if there's volcanoes going off, they should be here. Okay, here's our zircons. The top one is this Rain Valley Formation in southern Arizona. The bottom one is the Kaibab Formation in western Arizona. These blue diamonds are our magic 275 places. Not much there. Don't worry about the red squiggly lines. What you're after are these little tiny, sort of blue-green squares. If you look at this blue-green square down here and you move over to the side, you see you've got 2 grains. 2 grains is not telling you anything about a whole bunch of volcanic zircons in your sample. In this one, in the Rain Valley Formation, there's 1, right? So we have this interesting problem that if you go to the continent side of the volcanic arc, there's no volcanic arc. Not sure why. So what we know is that depending on where you are, either the strike slip fault was juxtaposing continental crust against ocean crust or continental crust against continental crust. There's really nice evidence of the arc until you walk behind the arc, at which point it's more of a problem. Super quickly, to get to where we do know about an arc, we're going to move ourselves up to the lower Triassic rocks, and Steve did talk about these last month. So this is the lovely Buckskin Formation in western Arizona, and the top is our lovely Moenkopi Formation up on the Colorado Plateau here. And Steve talked about how we know that these are very likely the same unit. So I'm not going to go into that part of it, but I am going to show you more zircon data. And again, don't worry so much about the red line as these sort of blue-green boxes. There's a whole bunch of grains in here between 250 and 255 million years. So we're going to say that probably deposition happened not any earlier than in here, which is about 253 million years, give or take. But the other thing is to say, oh, well, look at that. There's this other little kind of a spike. It's not big, but it's there. So just store that one. That's at about 260, 262. It makes sense to say, sure, they could have come from, these grains could have come from Caborca, they could have come from El Paso terrane. Doesn't make any difference. So that's the Buckskin Formation. And here's the Moenkopi. And there's a lot fewer grains in the Moenkopi. So there's still this problem about how do you get things backwards onto the continent? Again, there's that 262 thing. And here's this 253 clot. So both of these seem to have depositional ages that are about 250, 253, 255. And there's something else going on at 260. So this is my little cartoon about what's going on. Is for whatever reason, the stuff doesn't get into the back arc. And I think part of the reason is that it's a lovely continental arc. Remember all that geochemistry you didn't have to listen to was telling us that this is continental crust here, all right. But there's ocean in between that and the continent itself. So you can think about Japan. You can say, oh, Japan's a perfectly like viable island, series of islands, lots and lots of gorgeous volcanoes, but it's a long way to China, right? But there's that basin in between Japan out here, the Japan Sea, and China, just upside down. What does it all mean for the subduction initiation? How are we going to solve this problem with this bit of data that we have? All right, here's what we're going to do. I am not going to show you a whole bunch of these pictures. They're very cool. They're almost impossible to make heads or tails of when you look at a figure like this. But Domeyer and Torsvik put together computer simulations. I was about to say animation. It's not really what I mean. Computer simulations of the globe, just using different parts, different aspects that people have come up with over time. We think that Caborca was sliding down along the west coast of North America, of Laurentia, so they can put in an arrow to say, there goes Caborca. So they've done this for the whole of Paleozoic tectonics. I find it a whole lot easier rather than to sort of look and say, well, now, okay, actually, I can see there's Africa, right? And here's North America, and there's Florida. Where else? You know, I mean, sort of, is this all the rest of North America, and what am I going to do? So rather than doing that, I'm just taking the parts that I need. So on this side, on the left side, I hope it's the left side for you, it is for me. The yellow arrows are taken from those reconstructions. This is the same picture that you've seen before with that fault coming through, that San Andreas-like fault, taking Caborca and moving it southward. There's not too much to sort of be understood from this, but maybe the easiest thing is to say, well, these plate motions weren't really affecting the margin very much at that time. So I've drawn this little sort of slice open the earth, pop down that piece of toast, and if you pop up the piece of toast, here's what you see on it. You see Gondwana. Oh, there's Gondwana. You see this ocean material, something that might be going to be Caborca, a fault, and North America. These little symbols, by the way, this circle with the dot in the middle is the tip of the arrow, and it's coming towards you. This circle with the cross in it is the back of the arrow, and it's moving away from you. So you can look at this thing and say, okay, this is coming towards me, this is going away. Okay, here comes Gondwana. Remember that Gondwana started in Mississippian time, way, like on the other side of Texas into the southeast of North America. And it zippered as it came westward. It isn't here yet, but it's getting closer. Okay, so here we are. There's this lovely strike slip fault, but maybe there's some stresses. Maybe there's that external force being put, pressure being put onto that fault zone. That's what these little squiggly lines are. By middle Permian time, by 280, 275 million years, we've got something, right? We now know, if we are down into our magic 275 number, we now know that we've got a whole bunch of magmatism down here and a whole bunch of magmatism up here. So we've achieved subduction. We have achieved our goal. We have subduction. But it's just about, funnily enough, it's just about the time that Gondwana is starting to make its approach and smack into North America there. So here's sort of the final, the 260, right? And what we would say is by 260, and there is some evidence in a number of places, by 260, subduction was probably alive and well along this entire margin here. It was much later by the time you get up into the Northern Sierra. That's a different talk entirely. But at least here in southwestern US, this is a good sense that subduction was going on. All right, so these are the final words about trying to figure all of this out. How do you cause subduction? If we started at the El Paso terrane up in the north there, and we say, well, probably that was just, it has all the good sort of evidence of simple, if it can be simple, forced initiation. so that the oceanic plate was just kind of forced underneath the continent along that fault. To the south, there was Gondwana coming up, and maybe that transcript strike slip fault, that San Andreas-like fault, couldn't do much with Gondwana. It couldn't make its way into Gondwana. And so when Caborca hit Gondwana, it stopped. There was nothing else for Caborca to do. It couldn't plow into Gondwana in any way. This is a sort of a philosophical question that I don't particularly have an answer to. Is there, if we have a fault in between two little bits of continent, as opposed to a fault between continent and ocean, does it act the same way? I don't know. Maybe it does, maybe it doesn't. And then finally, the mystery question is, what was going on behind the arc there? What was going on in the Kaibab and the Rain Valley and these other sediment, even to some extent in the lowest Moenkopi? Some people could suggest that, well, maybe subduction was going the other way. Instead of going underneath the continent, maybe subduction was going down underneath the other land masses and that Panthalassan ocean. I don't take any pleasure in that. I don't take any comfort in that. I don't think that works. The only other thing to say is, well, maybe it was very, very topographically low arc. Arcs don't necessarily give us Cascade volcanoes or Andean volcanoes. In some places, the arcs are very, very low topographically, and maybe that's our best option there. So I want to close off just by saying thank you to any number of colleagues and my students who are continuing to do amazing, great work throughout the whole entire stretch of this arc, this Western North America, and the colleagues who have helped, well, give me most of the information that I've summarized to present to you. And I will very happily take questions now.
Great, thank you very much.
You want me to stop sharing?
Yeah, up to you. If you think you'll be referring back to the slides, then you can keep up. Sort of your call.
Either way, okay. We'll do that.
Thanks for adjusting your title to be accessible. A conversation that we had back and forth. I think it showed the talk too. So, folks, please put your questions in the Q&A, and I'll read them off. I see we've got one already. Aaron Alexander asks, do you need a larger sample size to get more zircons for your continental crust samples, or are there other problems with obtaining zircons?
That's a really nice question, When you're looking at something like the Kaibab limestone, a limestone sort of by definition shouldn't have zircons in it, right? Because it's a chemical sedimentary rock. It's dominated by precipitation and not a whole lot by transport of stuff. The Kaibab itself does have a lot of sediment in it. You are right that if I collected many, so the samples I collect are usually, I'd say 10 kilos or so. And in a sandstone, that's plenty. In the Rain Valley Formation, that was, I had hundreds of zircons out of that Rain Valley Formation. Same with the Moenkopi. So a limestone would be more, but in the other samples, my guess is that if they were there, they would have shown up, honestly. You can look a bit by shape as well. In the Moenkopi samples, some of them were just lovely, like they looked like sharpened pencils, honestly. And so they were clearly volcanic zircons, but just not a lot of them. And yeah, I think the easiest answer is just that the zircons don't make their way to those sites of deposition.
Okay. Another zircon question. Jane Rector asks, what processes would affect the age of zircons you test in igneous rocks? Why would they show a wide range of ages?
Excellent. So when I showed the slide of the Los Tanques Pluton, it's funny, there's a couple of different answers to your question. When I showed, there's all these little red splotches, and here's the one I like the best because those red splotches are very narrowly concentrated. Part of that is because we were using two different machines. So the ones that they were more dispersed were analyzed by shrimp at Stanford University, and the more concentrated ones were analyzed by ICP at the University of California in Santa Barbara. And there's other techniques that you can also do, and they get into some chemistry, but I think one easy way that I might be able to answer that is to sort of to say two different parts. One is that when a rock is deformed, if it gets to high temperatures, then these high temperatures can really affect what's going on in all parts of the rock. And if they're high enough temperatures, it can include the zircons. They can start to have sort of like open systems so that the uranium can come and go and the lead can come and go and can wreak a bit of havoc. But one of the things you can do is very much akin to getting your teeth drilled, which is to say that you can treat the zircons with a little bit of hydrofluoric acid before you analyze them. And that gets out the rot, all the decay, all the cavities. And then you can, again, pull those numbers in a lot more tightly, which is what happened to that one sample that I prefer very much. So I don't know if which half of that might be the question you were answering.
Yeah, so she's really asking why they have a wide range of ages. So I think you're touching on that.
Okay.
Let's see, we got another question here. We got a number of questions. So Abdel Hafiz asks, when Gondwana joined the North American continent, did it have any effects on the initial subduction slope?
When you say slope, do you mean the actual, was it steep or was it more shallow? Is that what you mean by slope?
If Abdel wants to type in a little bit, he can. Let's move on to another question.
Okay.
We'll circle back to that if he asks. Addison Sherman asks, are other volcanics in Arizona like the superstitions not related to the volcanic arc?
Another spectacle. You guys are really good. The superstition volcanics are much younger. And so it's sort of a whole different sort of tectonic setting trying to get at those. Yeah. So I mean, it's yeah, it's probably the easiest to sort of to leave it at that, but they are not related to that initial subduction setting at all.
Okay. So this one is a little more technical. I'll try to get the vocabulary right. So Tim Demko asks, he says, Meiji Fan has shown that ashes really start increasing abundance during the late Wolf Camp and then going gangbusters in the Leonardian in the basal deposits of the Delaware and Midland basins to the east. Is this the arc kicking off?
Tim. So one of the things that I decided not to talk about at all is what might have been going on much farther to the east. And there is something called the Mexican, what do they call it? The East Mexico arc that is set, and a lot of it is, it's an unfortunate arc. A lot of the dating of it was done a long time ago in relatively imprecise methods. However, he's right that Machifan has found a whole bunch of these things, and there seem to be, and actually I found some of those zircons in the Moenkopi formation. But the problem, I once gave a talk about the Moenkopi, and I showed this sort of peculiar Moenkopi data I have. And the biggest problem is when you look at wind directions, it's not easy to get from East Mexico over to southern or central Arizona or western Arizona. It's just, it's very difficult. And the rest, I mean, there's like these lovely plutons right there in Mexico, which are a whole lot closer, and just topographically that makes it easy. So I don't know if that's what you're sort of getting at, Tim, but I think it is sort of, the ash beds are the best evidence for that arc that there is. And yeah, and then after that, it's sort of like, well, how do you get them from A to B if the wind is blowing the wrong way?
So it looks like Steve wants to comment. Steve, feel free to.
Yeah, I can't ask in the Q&A, but Nancy, this may be kind of a silly question. I don't think I heard you use the word transpression at all in your talk. And I was just wondering, when you're bringing up Gondwana, when you have that jamming, is there any chance I could have induced any kind of kinks in the transcurrent boundary that might have influenced the initiation of that?
Absolutely. You would have to ask your students sort of how way too overpoweringly jargonish the talk was, but I was just sort of avoiding, I had to sort of choose my poison. And so
I thought I saw that, but I wanted to make sure that was
no, absolutely. Okay. I mean, I think that makes a ton of sense. The thing that's kind of weird is that, it's slamming its way up like this would tend to sort of move things the other way. So I'm not sure how those reconstructions, those plate motion reconstructions actually accommodate Gondwana. I think to some extent they were put together without recognizing how far west Gondwana actually was.
Okay. It was not a jargony talk, I can assure you. Thank you.
So any further questions from anybody? We still have a few more minutes. We could cycle back to Abdul's question. He did not elaborate. So you're free to interpret it as you wish if you want.
So
Oh, we do have another. When Gondwana joined the North American continent, did it have any effects on the initial subduction slope?
Yeah, so I guess, I mean, I would want to answer the question that he was actually asking.
Yeah.
So it would have, gosh, I mean, it would certainly, that collision would certainly affect the plate motions, and the plate motions would absolutely affect sort of the angle of subduction, the orientation of subduction, very, very much. By the time Gondwana collision got around to Western Mexico, to Sonora, it was not as sort of powerful. I'm not sure what's the best expression to use, but when it hit the region, the southeastern part of North America, it really hit. And so it's sort of, well, I guess from your perspective, maybe it looks better like this. It just sort of like it rolled its way in. And so people refer to a sort of a soft collision by the time it made its way to Sonora, and possibly farther west than that.
Yeah, Abdul just chimed in. He said what he means is more the subduction angle.
So the actual slab itself, yeah, I think, so the part about that, I mean, it's a really fair question. The subduction angle can be controlled by how fast plates are colliding, how old that slab is, how fast it's, I mean, just like a whole myriad of things that are specific to that situation right there, that overriding plate, that downgoing slab. And so how much this sort of nudging really affected it would be hard to say, because it wouldn't affect the age of the downgoing slab, but it would absolutely affect the motion of those two plates. I mean, you can have the best sort of jamming into each other, but one might be going that way and one might be going, well, you can't see anything with the background probably, but the point is, the absolute motion of those two plates is important too, and Gondwana smacking into Laurentia would have affected those absolute motions. So yes.
All right. More questions coming in now that people see the opportunity. So John Morgan Christoph asks, he says, perhaps a little less technical than Tim's question. When I got my geology degree back east, we learned about similar subduction initiation events around the Alleghanian orogeny. I was under the impression that the whole continental collision occurred more or less continuously from Nova Scotia to Sonora. And your presentation seems to indicate it's more discontinuous and discrete. Which end member scenario is closer to the truth?
Okay, so there's two things. One is that if you take the creation of Pangaea, then that would not be by itself creating an arc, a continental arc or a volcanic arc, both. So a lot, that collision was so much of like creating this big, huge fold and thrust belt. Whereas on the western margin of Laurentia, that's where the subduction started. So I might be misunderstanding what you're saying, because I don't know if you're sort of referring to some of the older volcanism that's all along eastern North America, and sort of how that began. And again, I think if you could get down to really the oldest evidence of subduction, that could well change not only between sort of like Georgia and Sonora, or between Nova Scotia and Georgia, just sort of anywhere that you would look at where a volcanic arc developed. My guess is that in most cases, I bet you'd find that it's sort of like a little bit piecemeal, a little bit here and there, without necessarily, there was some period when people suspected that in Western North America, it went from north to south. And then we found all this stuff in Sonora. It's like, well, no, it didn't, but I mean, so there is this sort of like, it's like looking at the San Francisco volcanic field. It's like, well, it's younging from west to east, but it's not absolutely moving like that.
Stephen Reynolds asks, Did you get any arc zircons from the Kaibab in northern Arizona or only in western Arizona?
I haven't done it in northern Arizona. I've only collected where we were in the Palins.
All right.
So I
So
don't know.
If Steve, if you want to, I don't know if Steve was going somewhere with that question. Feel free to follow up if you want. Joseph asks, can you elaborate on why a topographically low arc may explain the lack of volcanics in the back arc basin?
Yeah, okay. That's completely fair. I just sort of busted through that one. So the idea would go, I have to confess, this is a little bit of, I want to find an explanation to fit the data, which obviously is what you're going to do in science. But the point is that, you know, if it's a high standing arc, then there better be, that arc better be coming apart in just about all directions. Right? I mean, there's evidence of Cascadian volcanism to the east of the Cascades and to the west of the Cascades. If you're underwater, which this arc was at the time, it was very much, I mean, the pictures all show, you know, this landmass called Caborca, but the arc itself was almost for sure underwater. Then you're more reliant on ocean currents, for example, sub-basins on the ocean floor, but I still would tend to think that, yeah, okay, so here's another thing. Low standing, if it was a high standing arc, I think it was below sea level. It doesn't have to have been much below sea level. If it was a high standing arc and it was giving you cascade volcanoes, I think you could easily say, well, there should have been a bunch of subaerial eruptions moving zircons all over the place. So if it's low standing, you don't have to move things as far. And I think it's probably just easier to sort of create currents and topography if you don't have a whole lot of topography to begin with that would move things in one direction or the other. You'd say it's like facing towards the ocean side.
All right. Tim Demko comes back and says the paleogeography of the plate margin has important implications for the presence or absence of a Mediterranean type outflow of a saline bottom current out of the Delaware Midland evaporative seas. So this is freaking cool, he says.
Tim, I haven't talked to you in way too long. Yeah, so I should, I mean, I have to say that, you know, I don't know that much. I know what Manchi's done, and I've talked to her and, you know, read stuff for her, pre-publication stuff for her, and, you know, like that. But I don't know those kind of details in the slightest. How's that?
It is what it is.
Yeah.
I just thought that, I mean, in the interest of time, we should probably wrap up. I just thought that was it's kind of fun to end a talk on the phrase. So this is freaking cool. So
Thanks, Tim.
So thanks for the comment, Tim. Thank you, Nancy, for a really nice talk.
Thanks very much.
I mean, the vibrancy of the questions, I think, tells you that you engage people who are paying attention and asking lots of good questions as a result. So thank you very much.
Thank you. I really appreciate everyone's attention.
And we look forward to seeing you again here.
Great.
In person the next time.
Good.